In 1982, there was a conference held in the United States. It was held in Snowmass, Colorado, where high-energy physicists from around the world, but mostly from the United States, got together and planned on what the next accelerator would be. Came out of that was the very strong physics interest to make a very high-energy proton-proton collider. And this led in the United States to a project that was called the Superconducting Super Collider. It led in Europe to a project that was called the Large Hadron Collider. Well, it turns out that the Superconducting Super Collider in the United States met its political fate in 1993, but the Large Hadron Collider continued in Europe, and it then developed into a machine which now is operating, and it's producing a huge amount of data, and it is part of that dream of going to the very high energies needed to study questions involving the Standard Model and looking beyond the Standard Model. It's always been the story in high energy physics, built into its name, that the higher the energy you have, the better off you have. And so physicists in high energy physics are rather primitive animals. They like to make huge collisions and very high energy collisions and then sort of stand back and see what they produced. And the theorists, of course, are more refined than the experimentalists. They make various predictions about what would be needed, but the basic exploration has always been go to the energy frontier, make an accelerator which is the highest energy possible, smash protons against protons at the highest energy, build a detector so that you're able to study the debris from these collisions, and then see if you see something that's different, new, exciting, strange. So that was the dream. And the dream didn't happen in the United States, but it did happen beautifully in Europe. And we members of the US community were very lucky to be able to join our European colleagues in doing experiments at the Large Hadron Collider at CERN. Well, making a proton-proton collider is the cheapest and most practical way to get to high energies, because protons are relatively easy to accelerate and they're relatively easy to collide and they're abundant. Electrons and positrons are beautiful, very clean final state when they interact, but they're very difficult to handle at high energies. So it was obvious that the experimental community would go into making a proton-proton collider. The collider in Geneva, Switzerland, the so-called Large Hadron Collider, is able to, at the present time, collide protons and produce an energy in that collision which is about 10,000 times the mass of the proton. Now, you don't realize all 10,000 of these times, but you can realize about maybe 1,000 times the mass of the proton. So in this, this fundamental tenet of high energy physics, you want to probe the energy frontier. Now, at the Large Hadron Collider, we have a machine that has sufficient energy to produce objects, if they exist, which are on the order of 1,000 times the mass of the proton. So that was really the very interesting part of the exploration. It's like building a really big telescope and then looking at the sky, and you're not exactly sure what you will see. We built a very energetic proton-proton collider. We're not exactly sure what we'll see, but it's a big exploration. So what has been done to date is to use these proton collisions to try to see if one particle, which had not yet been detected until it was announced in July of 2012, and that is the Higgs Boson. The Higgs Boson is the very pinnacle of the Standard Model. It was predicted. Higgs wrote papers way back in the early 60s. There were a number of people who contributed, but Higgs is one of the prominent theorists who proposed the idea that there exists this particle that is now called the Higgs boson. It has no spin. It has an even parity, so it's a very symmetric, very simple, very vanilla kind of particle. The only thing that it has is that it can interact with itself. It's like a snake eating its own tail, and this causes theorists nightmares. It can also couple to other particles. It can couple to top quarks, it can couple to bottom quarks, it can couple to muons, it can couple to the vector bosons, the W's and the Z's. And all of these couplings, all of these interactions are predicted by the Standard Model, including the fact, as I said, that it has no spin and no parity, or even parity. So it's a very interesting beast. Nobody knew exactly where it would be. One of the main experimental thrusts of this physics program at the Large Hadron Collider was to produce the Higgs. First of all, to be able to see whether or not the Higgs exists, and then, if one is lucky enough, to actually produce the Higgs and study its properties. The Higgs is the very pinnacle of the Standard Model. It was predicted way back in the early 60s, and without the Higgs, there would be a number of difficulties in the Standard Model. There would be cross-sections, for example, that would become infinite at very high energies. There would be lots of other things that needed to be explained. But the Higgs itself explains a tremendous amount. So discovery of the Higgs was one of the outstanding questions of high-energy physics. Well, in July of 2012, there was sufficient data accumulated at the Large Hadron Collider in 2 experiments. One of them was the ATLAS experiment, the experiment I'm working on, and the other one was the CMS experiment, where my colleagues at MIT and other people in the United States and abroad are working on. These experiments are complementary, but they both detected the same particle, roughly the same mass, and it was a tremendous success and received a great deal of press coverage and so on. After the initial discovery and the announcement in July of 2012, more data were accumulated on this particle. And the new data indicate that the particle is most likely really the Higgs particle. Namely, it seems to have all of the right couplings, it seems to have the right spin and the right parity, although as an experimentalist one is always skeptical and you always need more data. So the project will continue in the years to come to study the properties of this particle. But it exists, as I say, at the very pinnacle of the Standard Model, and it's the one particle that sort of ties the entire picture together, and it was a tremendous coup of theory as well as experimentation to be able to discover it, and a tremendous success. The question, of course, is success should breed success, so what are the questions beyond that? And the Large Hadron Collider, by the fact that it has the highest energy in the world, is now an experiment and a facility which gives one the opportunity to continue the exploration, for example, to see whether or not supersymmetric particles exist. These are the companion particles with different symmetries from the Standard Model particles, or whether there is something which is not predicted by the Standard Model. So the search goes on. It's only beginning. It's very exciting. It will go on hopefully for the next 10 or 20 years at higher energies and at higher intensities with more and more data to answer some of the outstanding questions. But so far, it's been a tremendous success as a confirmation of the Standard Model to say that the Higgs exists, but now the question is what beyond? The discovery of the Higgs doesn't answer a lot of fundamental questions of the theory. If there's nothing more than what is called the minimum Standard Model Higgs, then because the Higgs can interact with itself, there are radiative corrections that have to be accommodated. So, for example, the Higgs mass is generated by itself. It's again like a snake swallowing its tail. It's sort of a redundant, self-involved, convoluted theory. And to get a finite mass of the Higgs, theoretically, we've measured it experimentally, the theorists now have a great deal of trouble explaining why its mass is 125 GeV and why it can be calculated to exquisite precision by the theory. Because it can couple to itself, there are these higher order corrections where the Higgs can couple to itself, it can couple to Z bosons, W bosons, it can couple to all sorts of other things. And these couplings can then be expressed mathematically as a long series of terms. There's one term, the lowest order term is a particular finite value. It's compensated by another term, but not exactly the same value. And then there's another term which compensates the second term, and another term which compensates the third term, and so on. And this series goes all the way out. And if it went all the way out to where quantum mechanical effects show up in gravity, this is an exquisitely high energy, it's so the Planck mass scale, then you have to do these cancellations in this long series to infinite precision, something like 1 part in 10 to the 32. I've forgotten about that, exactly the number, but it's considered to be unnatural to have such exquisite cancellation. And this is causing theorists a dull headache, and it's causing them a long, long headache, and it's lasted for 20 or 30 years, if you can imagine having a headache for 20 or 30 years. But, we all suffer from them in this particular way. And that's sort of the edge of the theory. Nobody knows exactly how these cancellations happen and why they're done in such exquisite numerical precision. So this is the grounds for other extensions of the Standard Model or other aspects of the theory, and this is, again, the cutting edge for the experimentation. One explanation would be that there is supersymmetry. Supersymmetry addresses this exquisite cancellation and says, oh, well, it's perfectly natural because the supersymmetric particles then participate in this series of these higher order interactions, and they cancel each other, and by the fact that there's so many parameters in the supersymmetry theory, the cancellation is relatively easy. And that's one explanation. Another explanation would be, well, maybe the Planck mass where quantum mechanical effects come in and gravity is too high in energy, and maybe there are other energy thresholds and we don't understand sort of the extension, the high energy behavior of the theory. Or there can be other things, such as space and time could have much more complexity. Instead of 4 dimensions, there could be 10 dimensions, and the other 6 dimensions could be compactified. They could be small dimensions, and maybe this explains the weakness of gravity. This explains maybe something to do with of how the Higgs mass cancellation and its series, the snake eating its tail, is able to come out with a finite number. So it's very interesting. Before the Higgs discovery, the focus was the Standard Model Higgs through electroweak interactions, neutrino scattering, E plus E minus annihilation at the Z pole. These higher order corrections all predicted the mass of the Higgs, and it was something of order 65 times the mass of the proton, or maybe a few hundred times the mass of the proton with large errors. It was discovered at 125 times the mass of the proton, roughly, just sort of where it was predicted. And now everybody's looking around and saying, well, that's very nice, but what's next? The energy of the LHC will be upgraded to a higher energy, and also the intensity of the beams will be upgraded to more intense beams. So one would be able to probe to larger mass objects as well as more rare processes, given more beam and more data. So the exploration will continue, and it will go on for the next 20 or 30 years, hopefully. And it'll be quite interesting to see what happens, because Again, we had this wonderful prediction of the Higgs in the Standard Model. Now what will be discovered is something which is beyond the Standard Model. And it hopefully will open up a completely new field of physics. Hopefully it'll be a cornucopia of interesting phenomena that experimentalists and theorists can try to understand. And that's what one hopes for in this exploration. And it will go on, and I think that I hope it has a reasonable likelihood of revealing something new and exciting.